Welcome, everyone. This is the WiNDC summer course. Very pleased. I don't know if it's on my screen here. Anyway, let's get it. Okay, get it? Yeah, fine. So we're here for 3 days. The objective is to have sort of 3 separate days on separate topics, sort of to introduce general equilibrium modeling and the use of the data set and extensions of the standard framework is sort of the 3 topics. I was really pleased Jim Markison was able to come in to lecture for the first day. And so his lectures will be largely based on the survey piece he just published in the JGEA this year.
It was December
of last year.
Anyway.
And then tomorrow we'll talk about sort of doing data analysis with the WiNDC framework. It's more about, so today is more about what's the motivation, what are the structure of the models, what's the underlying sort of logic of what we're doing. Tomorrow is how do we actually do it? So the idea is to do some simulations and work a little bit with the data set, more hands-on type stuff. And then on Wednesday, we'll talk about overlapping generations modeling. So it's a little bit more, these are separate, it's not intended to be sequential, it's more just we're going to jump into something new on Wednesday. And this was, we've talked before about building dynamic models with WiNDC, and our build stream is designed for that purpose, and this will be an opportunity to talk about. So that's where we're at now, and I'm really happy to have Jim Markison in to talk to us. So Jim, it's all yours.
Okay, and people can interrupt questions. Yeah, do feel free to do that. Okay, good morning, everybody. I'm Jim Markison, University of Colorado Boulder retired, sort of, which means I'm not getting paid, but other than that. And most of my work over many years was in theory, and there was a point where I got really frustrated with analytical methods in microeconomics. They were way too confining. So I started turning to simulation analysis as a theory tool, which was very uncommon at the time in economics. You either did analytical models with pencil and paper, or you did, econometric estimation. There wasn't anything in between. So over the years, one of my contributions was to try to think about ways to incorporate added features into models, which at that time were very restrictive. They were basically perfect competition, constant returns. Models where interior solutions were basically imposed, and try to generalize those by putting in everything like increasing returns to scale, imperfect competition, trade costs, public goods, externalities like pollution, and so forth into these models. So what I'm going to do today is sort of walk through a process starting very, very simple, and kind of moving a little bit quickly, I guess, about how we do these things and how really even if one is going to use sort of off-the-shelf models and run them, it's really good to kind of understand, I think, the micro foundations of what's going on. So you may never make models yourself from first principles, but I think this is good background. And it's also great to experiment by just making little toy models and see how things can work and how they should be done in much larger data sets. All right, so these slides were one of the things I sent in my pre-course mailing. The file is called Madison Monday 1 PDF, and I'm just going to go through these now. And please do ask questions if there's confusion. So, as I said, the tools of economic analysis have traditionally consisted of analytical theory models. When I want to make fun of that, I call it paper and pencil economics. I did paper and pencil economics for 30 years. Econometric estimation and testing, And simulation modeling is a little bit newer, really, in economics. And it's really a complement, not a substitute for 1 and 2, in my opinion. And what it does, it greatly increases the reach of theory to problems that are analytically intractable. And it extends the economic usefulness of econometrics. People are now estimating structural models, and then they're using tools that I can develop here to then do counterfactuals on their structural models. And that's become actually a big business, I think, in economics right now. So it's typical that economic models are done in one of 2 ways. Small models as a constrained optimization problem, and B, an economic equilibrium problem, which is typically a square system of equations and inequalities and unknowns. I have a quote here, which is my motivational quote for the morning. I always put this up. I asked people to guess when this quote came, and unfortunately, I put the answer up here from John von Neumann. Many branches of both pure and applied mathematics are in great need of computing instruments to break the present stalemate created by the failure of the purely analytical approach to nonlinear problems. He was talking about partial differential equations, but hey, I like this quote a lot. And when theorists object to using simulation as a theory tool, I always trot this quote out for them.
So on point 3, though, Jim, just one of the things that's interesting here about the simulation modeling is, you emphasize the extension, the problems, but one of the things that's a real virtue of having analytic models that correspond to the numerical models is that we can double check our intuition. In other words, to say the thing is that it's not like simulation model is really not a replacement for analytic methods. It just helps guide you as to what matters. Right? You can always build an analytic model where if it's uncalibrated, you can make all sorts of assertions about the relevance of a particular perception or mechanism. Yeah. And the great thing here is this ability to identify what is the analytic model is relevant here. And otherwise, so it's sort of just an add to point 3.
Yeah, okay, great. So again, my frustration, it was sort of at the end of the 80s, and then a great thing happened to me. I met Tom Rutherford, who introduced me to GAMS. But some analytical methods, as I said, quickly become intractable. There's a number of reasons. Functions or equation systems have no closed form solution. The large dimensionality of the problem you actually want to work on. The correct models consist of nonlinear weak inequalities, whereas lots of calculus-based analytical methods, comparative statics, for example, just can't deal with those corner solutions. You hit a corner where something goes to 0 or the opposite on some variable. And large changes in parameter values. Another thing I should add is a lot of analytical methods only give you qualitative answers. Like, okay, the derivative of variable X with respect to parameter alpha is positive. Okay, let's go home. Well, how positive? How big? So my approach was to begin to use simulation analysis as a complement to analytical methods. Structure of a typical model in economics is models based on the assumption of optimizing behavior by different agents in the model, consumers, firms, and governments. But generally, the model cannot be written as a simple constrained optimization problem because there's multiple different agents doing their own optimization in the larger environment. You can't just say maximize X with respect to all this constraint set because different agents are pursuing their own optimization problems. So an economic equilibrium model, what it does is typically it's embodying optimization at the level of the agent. So the model becomes an n-by-n equilibrium problem where the individual equations or weak inequalities are derived from the optimization problem of that individual agent. So households, they optimize their preferences with respect to a budget constraint, and that yields demand functions, which become one of those things. So the optimization is built in at the level of that agent. And the same thing for firms. They're minimizing cost or maximizing profits subject to their technology or other constraints that they face. And so then you get supply functions, cost functions that embody that optimization at the individual level. Okay, I circulated the pre-course notes, and so I don't want to go through that, but there are a lot of underlying pieces of mathematics that are extremely useful for creating these economic equilibrium problems. One of the most important ones is the Karush-Kuhn-Tucker theorem, which basically converts a nonlinear programming problem into a square system of equations and unknowns, including these slack variables that I discuss in those notes, that allows for the computational corner solutions, which is very important in so many economic problems. And I'll give examples of that. The implicit function theorem basically says a square system can be solved for explicit functions, endogenous variables, each as a function of system parameters. Once you get past simple problems, I've never actually been able to make that work. And in some sense, if you're doing numerical simulations, there's no need to get closed form solutions for problems. The envelope theorem and Shepard's lemma is extremely useful, as you're going to see today, because so for a household or a firm, once you solve for a cost function, you can directly solve for demand function, firm's demands for capital and labor, say, or a household's demand for goods, because they are just a derivative of the cost functions based on Shepard's lemma. And everyone has this. I have a little story about this. I teach second or third year PhD students numerical modeling, and they've had lots and lots of microeconomics in first year, going into second year, and I say, do you know what Shepard's lemma is? And they go, yeah, we had that in micro. We didn't do anything with it, and they have no idea. They can't tell me what it says. All right, and it turns out it's extremely useful in what we're gonna do in numerical simulation model. So the notes do go through that, and if you haven't had a chance to do them, and you find this interesting at the end of our 3 days, go back and look at them, and you'll see why it's so key. I guess I'll be showing you why that's so key today. Okay. So just a little bit more pep talk about why I'm doing the things I'm doing this morning. I'll call that dimensionality, inequalities, and bounded variables. Dimensionality, big numbers of equations and unknowns, and nonlinearity and simultaneity make models hard to solve analytically past very, very small models. So someone who insists on analytical methods, the key thing is, get the model down to 2 equations and 2 unknowns, and then maybe you can solve it explicitly. But even some of the very simple models in international trade, such as the Heckscher-Ohlin model, which has 2 goods, 2 factors, and 2 countries, really doesn't have an easy analytical solution to it. And people derive qualitative properties of the model, like this Stoper-Samuelson theorem and the Rybczynski theorem, but they're not actually general equilibrium results. They are partial equilibrium results. Secondly, economic variables are typically bounded. Prices and quantities are non-negative. And economic equilibrium conditions are then weak inequalities. They're not equations. So examples are what goods are produced, what technologies are used. In an equilibrium, maybe you produce certain goods, or you use only 1 or 2 of the set of available technologies. Think of making electricity. Some things are just slack because they're too expensive in equilibrium. In international trade models, what trade links are active in equilibrium and how do those change? A lot of early GE modeling were not able to handle switches from active to inactive or the other way around. Assumptions were always imposed, like what's called the Armington assumption, that guarantees an interior solution. Okay, but you're really throwing out a lot. An actual trade matrix, 3-dimensional one of exports of good I from country J to country K, has lots and lots of zeros in it. And they may not stay zeros. A lot of those may go active as you lower trade costs, for example. So you really want to be able to handle these things. Also some issues with prices, and I'll get to that a little later in the morning. There's cases where a good may not have a positive price. I'll kind of postpone that, but things like quotas or emissions permits can go slack, right? You have such a quota, but the economic equilibrium is that's non-binding, right? Or you have too many emissions permits, so the market price of emissions permit is 0, things like that. So traditionally, older general equilibrium modeling, good economics was often sacrificed in order to ensure interior solutions where all variables are positive, all prices are positive. So the way that the basic idea about being able to incorporate these things into an economic equilibrium problem, a simulation model, is the notion of complementarity, or the KKT conditions. So that's Karush-Kuhn-Tucker from underlying nonlinear programming. So the fact that economic variables are constrained to be non-negative puts restrictions on the system so that equilibrium conditions are weak inequalities. Each inequality is associated with a particular variable called the complementary variable. If the equation holds as equality in equilibrium, the complementary variable is generally strictly positive. If the equation holds as a strict inequality in equilibrium, complementary variable is 0. And I'll go into that a little bit more. So the solver, and the way GAMS is constructed, and the solver in GAMS for systems of inequalities are called MCP, mixed complementarity problem, is actually based on a piece of mathematics that turns out to be very useful. It's not some ad hoc method. In GAMS, there's several ways of formulating economic equilibrium models, and I'll show you a little bit about this morning. Nonlinear program, and NLP, is a constrained optimization problem. But in a constrained optimization problem, you can only maximize one thing at a time or minimize. You have a variable that's being. Economic equilibrium problems, as I said earlier, there's lots of optimization going on by firms and households. So you can't really formulate a general equilibrium model successfully as an NLP. It's not going to work. So the MCP solver in GAMS, which was written by Michael Ferris, called PATH, who is University of Wisconsin person. He actually came to Colorado, right? He spent a sabbatical with us. And yeah. So Colorado has a little piece of the action here. So this is based, comes straight out of KKT. It shows a square system of equations and inequalities and unknowns, matched inequalities and variables. And then something we won't go in, but I have in my portfolio of examples on my website, MPEC is mathematical programming with equilibrium constraints. And it's basically a nonlinear programming problem where the set of constraints on the maximization or minimization problem is itself an MCP. Okay? And so I've shown how to use this in some examples on my website for finding an optimal tax. So you have a general equilibrium model, there's a tax in there. You want to know the optimal value of that. Well, you could just keep iterating and try to look at welfare or something as a function of that tax rate. MPEC allows you to solve that directly. So you can say, maximize welfare subject to this general equilibrium model where the tax is an unmatched variable in the system. We call that what variable?
It's going to be, the problems can be non-convex, so you're not always trying to end up finding a solution. There are smart guys who work on it. The tools they provide.
An instrument variable. You're answering a different question. Okay, so this is just a little bit of notation. I don't want to teach GAMS, but I loved it when I first saw it because it's an algebraic language. And the character set is basically the ASCII character set, right? So, you look at MATLAB or Mathematica or Gauss, and, you have to learn all these weird terms and weird ways of doing things. And I really like GAMS because it seems so straightforward. Maybe that's because I grew up with Fortran programming, but it just seems so much more straightforward. You write out equations, for example, in ASCII character sets in a very, very straightforward way, just like you would write them down on pencil and paper. So this is just an example. This is an unconstrained optimization problem and shows how to use both the NLP and MCP solvers. So if you want to get an introduction, you can look through some of my examples here that start really, really simply. A GAMS program typically starts with a set of declarations, parameters, and sets. I haven't gotten to sets yet. Variables. If you just use the word variable, it means it's unconstrained. You can go from plus infinity to minus infinity. Non-negative variables are constrained to be non-negative. It's a shorthand. There's other ways of putting bounds on variables. You can put upper and lower bounds on variables. Because this is based on KKT, it just creates the slack variables and the equations that allow you to put these bounds on variables. So then equations are declared. If you don't have a comma after the name of a variable or equation, it is taken to be a comment statement. And so you see it appears in blue. This is made from GAMS Studio, which is I think a great introduction. You open GAMS, it goes directly into the editor. And you can, if you use a programmer's editor like Tom does, that's great. But this is just sort of a simple introduction, and all the color coding is there for you. You can change it as Tom does, but most of what I do, this is perfectly adequate. So then the way you write an equation or inequality is shown at the bottom of the slide. So the first equation, profits, ... That tells GAMS there's an equation. And then I've written it as the variable profit equals, and you don't use an equal sign, you use equal sign E equals. An equal sign is taken to be an assignment, right? So that goes back to Fortran, I guess, right? In Fortran, you can write x equals x plus 1. We don't do that in mathematics. That doesn't make any sense, but that's the way Fortran was written. You're saying that the new value of x is the old value plus 1. The equal sign is an assignment statement. It's not an operator. So profit equals value of output, the price, times labor to the alpha that was specified up there, where alpha is less than 1. We need some concavity in here if P is constant, minus W, which is the wage rate, times L. And then, if you're had a little economics, you go, oh, well, I'll just take the first order condition, the derivative of that with respect to labor. There's only one variable in this equation. Profit's a variable. And you can write the first order condition ... as W is greater than or equal to the derivative of that equation with respect to labor. So it's alpha P L to the alpha minus 1 minus W. Greater than or equal to here allows for this possible corner solution, which won't happen here because marginal productivity goes off to infinity as you have zero labor. But if W could be greater than the right-hand side in equilibrium, and that means it's just unprofitable. And so the correct answer is that L is 0. Whereas, the direction of the inequality in GAMS is always greater than or equal to. So that if it's strictly greater than, the complementary variable is 0. So this is probably what L wasn't probably the best choice of stuff. In nonlinear problems, and I'll illustrate this a little later this morning, it's quite important to set starting values of variables, because if everything is 0, which is the default in GAMS, then you can get stuck and nothing, you can't compute the solution. And I'll show you why that is. So the notation in GAMS to set a value of a variable but not fix it, that's different. That's .fx, is to just put a .l after the variable equals something, semicolon. We should talk about semicolons. I don't want to teach all of that. A lot of errors in GAMS when you start out are the missing semicolon. It tells the compiler that you're done with that statement. And if it's not there, it'll just keep reading. Okay, it's something that's the same. So L.L equal 1 is setting the initial value, but it's not fixing it. Profit.L is 1. That's probably not needed there. So this model can be solved in one of two ways. Profit NLP, that's the name of a model I've given it. That can be anything. Doesn't have to be the name of the file or anything else. It could be Joe, Sam. And then the notation is slash, and the equations listed that are in that model, in this case, there's only one. So slash profit slash semicolon, then the statement solve profit NLP using NLP, maximizing profit. Okay. So that's the GAMS code for doing that model. And after you solve a model, you can extract information from the solution and put them into parameters. And later we'll talk about dumping results to an Excel sheet or reading from an Excel sheet. PR profit is PR is a parameter, and you can set it equal to profit.L. Labor used in the production process, L.L, semicolon. Output is labor to the alpha, and then you can display the three variables. A lot of GAMS programs have so many parameters in them. It doesn't automatically display parameters after you solve. You have to ask for it. You don't want huge messes there.
Might show them the declaration for PR labor and output in the previous page, just so you can double check, see how this works. So you declare the parameter. If you put in a slash and a numeric value, that assigns an initial value to the thing. It's the initial value. You can overwrite it later, but that gives you initializers. Whereas output, labor, and PR are the hardware that have an initial value. They get assigned after the solution.
Yeah. You don't have to use this slash notation. After the list of parameters, after the semicolon, you could say P equals 2 semicolon. That's, I sometimes do that because it's just, I can go back easier. It's easy. All right, so then the second way of formulating this and solving this problem is to use the first order condition. You know, if you give this to a first year graduate student, that's how they're going to find the solution. So instead of treating this as an NLP problem, you can treat it as an MCP problem, as a complementarity problem. The declaration is model profit MCP. That can be any name you want, slash the names of the equations and which equation is associated with which variable. Okay, that's the dot notation. That is not used in the NLP problem. So you say FOCL dot L. That's not a good choice because I just told you that dot L also meant level setting. I should have had a different variable than L for labor. Sorry about that. This doesn't mean set the value. It means what is the complementary variable to that equation. Okay. So, and then the next line just says solve profit MCP using MCP. You're not maximizing or minimizing anything. So then you can extract again and display the solution. You can say profits equal the objective function profits. Labor is the solution value L.L, and output is labor to the alpha.
The variable profit doesn't even show up in its model because you haven't
Correct.
put in the equation profits. It's not.
I could,
Yeah.
but it would then be just sort of like a definitional. Yeah, so I could have put FOC.L comma profit. I don't think you need the comma anymore.
Anyway, the point is just that you don't have to have that equation. It's really not. You're just focusing on the first order conditions. The solver doesn't make you know what you're doing.
Yeah. Yeah. So I could have put the extra equation in there just as a definitional. Yeah. Oh, and equations and variables can't have the same name. So if you have an equation named profit and a variable named profit, you're gonna get an error message, I think.
And the same parameters can have the same name. So
Yeah.
all these things. That's one namespace for the model.
Yeah, okay. So an example then of a counterfactual is just giving a new value to a parameter. So let's increase the price of the firm by from 2 to 4. Was it 2? So initial value of P was 2. Increase it to 4 and solve the model again. You can do it again both ways. Parameter values are carried forward until you change. If you want to try something else, you want to remember to set that one back to where it was to start with. It won't do it automatically.
So the whole thing here, the point is your strength is often your weakness. So the strength of this Jim's illustrating here, you can do all sorts of stuff. It's like having a blank slate. You can do any sort of calculations. The disadvantage is you need to know sort of what you're doing. It's saying what exactly you're about it. And so there's always this tension between users of models and builders of models, and this is emphasizing this great set of alternative. You showed that you have two different methods for solving the same problem. That's helpful for understanding.
Yeah. So this model, when you open GAM Studio, it opens directly into the editor, and you can change things if you want, add to the model or change values. And then this tiny little green arrow up here is the run arrow.
You're not seeing that on the screen. You're sharing the PDF here, so you need to just turn off sharing and then turn it on again.
Yeah. Uh-oh, did I do something bad?
Now you share screen again and switch to GAM
Oh, it gives
Studio.
you the option?
Yeah. Do you have your GAM Studio open?
Yes,
Where is it?
it's right there behind. Oh, it's here.
Yeah. Okay. There we go.
Why don't you show them how you open the file? This is good.
Okay, yeah, I never know how much detail to go in, but you can say open and you can specify a path just like you would normally do in Windows. I've never used Apple, so that's up to you to learn. Using the word settings, you can specify a path down here in settings. Right here, I have the sort of default directory that if I say open a file, it will open this directory, basically. So, so I say file, I say open, and this is this first one. It's there. So then the run button allows you to run it, and there's options about what you want to see. Exit solution found. I've actually solved this model a number of times. And so like the first solution, don't need this there. What you want to look down for is the solution variables, and that's the profit level and the labor input. And then you can extract variables like profit, labor, and output, as I said. The second solve statement is doing it as an MCP with just the first order condition. I thought.
Oh, it's the same solution, value.
I know, but profit wasn't a variable. Well, I did what Tom, sorry, so the notes don't quite correspond to what's actually in the program. I did add the second equation dot profit, so showing the same thing.
You're just carrying one report. The whole point is that that's a surplus equation. It wouldn't have to be solved. So
yeah,
the bigger model, you may not want to put all your reporting in the model. You might want to solve the model and then do the reporting.
yeah, okay. And then same thing about display of the three outputs. And then a counterfactual experiment was to increase the price of the output, double it. And the new solution is that profit more than doubles, and students in microeconomics are taught that the profit function is convex in price. So there it is, verifying the analytical result and so forth. So I never know how much detail, to do, but I think this is enough that, you just have to do these things and make mistakes and stumble around and try to figure it out yourself and figure out how to correct errors and so forth. And I did also circulate the McCarl user guide which is explicitly for GAM Studio. So I think it's helpful. It's a little tedious at times, but it's way more than you want, but I think that would be helpful. Okay,
We've got the license file was distributed for GAM, so participants in the workshop have a 3-month license. Isn't it?
3 months license.
We have a 3-month license. GAMS is it's not freeware, it's expensive, but it's not overall relative to say Mathematica or other packages. It's about the same. It's had the same price since it was introduced in 1989. So these things are still, from my view, it's a relatively good deal. There's different people with different points of view about this stuff. You can get open source software and you basically don't have to do nothing, but then you don't really have somebody doing the one. So my view of GAMS is that you get a lot more than you pay for because you can basically you can ask questions if stuff doesn't work. These guys stand behind you. So I like that. But the best way to do this is to actually mess around with the model. Is to go get. I wonder if we could just take this guy right down CES version of the same model.
well, let me
Yeah,
go a little farther before we,
we'll get to
then I'll let you
exercise.
do that.
You can do all sorts of stuff with these models.
Yeah, I mean, I think the only way to really learn how to do stuff like this is trial and error. And I sort of made a nice side out of what started as self-teaching. I mean, I started making up my own little models, putting in added features that I wanted as a trade economist with strong interest in industrial organization, putting in imperfect competition and all kinds of added features to the model. And I just was doing it myself. And again, this is really, I think, very, very valuable, even if you're going to use off-the-shelf models to really understand things and to try simple cases. If you want to look at something, make up a simple model, get it to work. And I think you just understand what you're doing far, far better. Okay, so the second example just complicates this a little. It's going to be a constrained optimization problem. So a firm wants to minimize its costs, which is expenditures on capital and labor. That's sort of this, W times L, R times K, where L and R are variable. L and K are variables. W and R are parameters. And there's a technology, most of anyone with economics knows what this looks like. It's simply a Cobb-Douglas technology. Output equals labor to the alpha and K to the 1 minus alpha. So it has constant returns to scale. Yeah, W is labor price, R is capital price. So the parameters of this model are alpha. That's this exponent, this concavity parameter, or share parameter, rather, in this case, between the two factors of production. W and R are prices. Min cost is the minimum cost of 1 unit of output. Labor and capital are the optimal amounts of labor and capital. Oh, by the way, if you're going to use nonlinear programming, an optimization problem, maximize or minimize, the objective variable must be specified as a free variable. You can't say non-negative. Okay, it's got to be a free variable. So the word variables or variable, I think they both work, is the cost in the case of the NLP. Non-negative variables are labor, capital, and a Lagrangian multiplier on the constraint for X. equations are two equations, cost and technology. So in the optimization, you're going to minimize cost subject to the technology as an equation. And then there's first order conditions for the Lagrangian problem. And I wrote this down because this is exactly how a first year graduate student would do the problem. They write a Lagrangian equation where there's lambda times the technology constraint, x minus the technology, take the first order conditions. You have two equations and two unknowns, and analytically they would solve that by hand. Well, okay. Well, you could solve for W and R independent. There's no simultaneity there again. Cost would just be a definitional equation in that case. Okay, so formulated as an optimization problem, as an NLP, I call it, say, model cost NLP, two equations, cost and technology. And the command is solve cost NLP using NLP, the NLP solver, minimizing cost. Okay. So the technology equation is a constraint equation on the optimization problem. And then you can extract again the solution. What is the minimum cost? What is labor? What is capital? And display those as you go along. Formulated as an MCP, and again, this is how a student would solve it, or I would have solved this if, using analytical methods, is you take the two first order conditions of the Lagrangian equation and solve those. I've added in, those are, we need the technology equation because W and R are two equations and three unknowns. All right, so you need, this time you need that. So again, with the MCP, you need the dot notation, the name of the equation, dot, what is the complementary variable? And the technology is going to be complementary with the Lagrangian multiplier.
So just as a parenthetical comment on this class of problems, we've touched on one of the major class of problems, which is driven computational technology since the origin of time, since 1950s. This was the problem. This constrained optimization problem was used extensively during World War II. And Neumann and other people working on delivery on how to deliver goods to Europe. There was all sorts of logistics to be formulated in this class. And this was what led to is the discovery that this type of problem, actually a London problem, is a program that's a subset of this class problem, was what basically led to the development of computers. That's what paid for the early computers were just designed to run blending problems to better run refineries. That's where all the money was paid for the computing developers. And economists were smart enough to free ride on the petroleum industry. So it's the way you design the thing. Fine, we'll take that problem and learn how to use it for solving these other problems. And indeed, even today, if you look at the problem, one of the problems that make the news now about all these new computing technology, it's all optimization. Right? It's driving this. It's all identifying, these new technologies are all demonstrated using this problem class. So it's a very simple introduction to what's a very broad class of problems. Motivation for this.
Yeah. And again, on my website, there is, a model library. I need to update that with the latest versions, but lots and lots of different problems, all done fairly compactly and simply. How do you do this? How do you do a transportation logistics problem? There's actually a refinery problem in that list, along with some things that really piss off the econometricians. I say, econometric estimation is just a nonlinear programming problem. minimize the sum of squared error subject to these constraints.
But we should be a little bit, we need to be humble in the sense that what GAMS gives you is a very convenient and transparent means of writing down the problem. And it gives you access to powerful but generic solvers. And so that's the crucial thing, is these are generic. So you can open up your cell phone and ask for the route from here to the east side of Madison. And you get an answer back immediately, because that's a specialized algorithm for solving the shortest path problem.
Right.
If you formulate the problem in GAMS, you can solve the same problem. It won't be as fast as using your cell phone. But the beauty of this is you understand precisely what you're doing.
Yeah.
As a device for understanding the problem. It's very helpful. So it's generic technology that actually works on a large scale.
Okay. I don't think I need to run that one. Gonna run the next one. Okay, that's gonna be perfect, I think. Yeah, and then we're gonna have a break, half hour break at 10 Central Time. I guess, assume we have people from a variety of time zones.
Are there any questions at this point?
Yeah, anyone? Okay. Okay, this is the next thing is really going to illustrate complementarity. Those two problems are always going to have an interior solution, right? Because as the output goes to zero, the marginal productivity goes to infinity, and you're going to always, no matter how high the wage rate is or how low the price is, you're going to get some production. So they're not really, they were just a nice setup to show you how to do things. But I really want to talk about this notion of complementarity. And this is going to be done in a simple supply and demand problem. So this is a problem, a partial equilibrium model, just a simple model, supply and demand to a single market, two equations, supply and demand, two variables, price and quantity. The economic equilibrium problem are represented as a system of n equations and inequalities and then matched unknowns. I'm not sure you can do that. You can't really do this as an optimization problem because there's two separate optimizations going on at the same time. So X will be the supply of the good and has a price P. Supply curve exploits the firm's optimization problem. The first order conditions always tell you that price equals marginal cost is the optimal, I'm going to give you the optimal output. And the price equation is complementary with a quantity variable. So suppose that the firm's cost is quadratic. It's AX plus B over 2X squared. So then the marginal cost, take derivative of that, is A plus BX. So the solution to the firm's optimization or the supply side optimization problem is marginal cost greater than price. So that's A plus BX is greater than or equal to P. And that's complementary with X greater than or equal to 0. Now, just think about the economics of that. It may be in the solution that marginal cost is everywhere greater than price. So that's at the solution, that could be a strict inequality. If it's a strict inequality, you don't want to produce the good. You're going to be losing money. Okay? So that's kind of the intuition about what is the complementary variable here. Think of what happens if the inequality is strict. If you get the inequality in the wrong direction, it probably might compute an interior solution, but it might go off to infinity or something. So it's very important to let the economics drive which way that inequality goes. Marginal cost can be greater than price at the solution, but price can't be greater than marginal cost because that would mean there's an unexploited profit opportunity. That is not an equilibrium. So then on the other side of the market, the optimization problem for a consumer is maximize utility subject to a budget constraint. And that would give us something like a demand function. X is a function of price and income, where M is income. And we're just going to treat that as exogenous here. I'm not going to put that in as a variable, although we could, and then we could get some demand, shift the demand curve. So what is the inequality that goes with that? Well, it's X is greater than or equal to demand, complementary with the condition that P is greater than or equal to 0. So again, what's the direction of the inequality? Well, it may be that supply is greater than demand in equilibrium, and that means it has to be a free good. So, I can't charge you for the air in this room. I could say, Martha, buy some air here. You go, well, no, it's in excess supply. So the price is 0. So again, you have to let your economics drive what the complementarity relationship is and what is the direction of the inequality. Okay. Demand can't be greater than supply in equilibrium because that's not an equilibrium. The price would just keep rising until you choke off that excess demand. So this quantity equation is complementary with the price variable. So this is the problem then. I'm going to just suppress income and let the demand function also be just linear. So demand is an intercept minus D times P. So all the parameters are positive. That makes it easier to remember, I think. And so then the equation in the model, or inequality in the model, is X greater than C minus TP, complementary with P. So again, the direction of the inequality and which is the complementary variable is sort of, your economics tells you what that is. If you get the association wrong, you may be lucky and still get a solution. There's an interior solution, or it may fail to solve, or it may go off to infinity. You'll get an error message that says problem is unbounded, or something like that. Okay, so undergraduate economics, first year economics, supply and demand, boom, that's the solution right there. That's the quantity, that's the price. But this problem actually has 3 solutions, 3 possible valid solutions. And these are the solutions shown in the problem, okay? So the upper left shows first year economics undergraduate textbook solution. Interior solution gives you price and quantity at the intersection of the 2 functions. The upper right gives case 2, I call it, where the supply curve lies everywhere above the demand curve in the positive orthont. There may be a crossing at a negative quantity, but we're constraining that X variable to be non-negative. Okay, we don't know what to make of a negative X. If you didn't have complementarity, in fact, it would compute that. So if you had unbounded variables, it would return a solution where those 2 lines cross at a negative X. Okay, is this realistic? Yeah, sure. Think of there being a number of technologies to produce X. And this is one of the technologies. And given prices and the nature of the other technologies, this one is just too expensive. We're not going to use it. Okay. Even at 0, marginal cost exceeds demand price. Now we'll come back. That vertical little area there on the p-axis, I'll call S1, that's for slack variable. And that's very much a part of GANs in using KKT to solve these problems. It's going to report that, what that S is. That is also has a nice economic interpretation. It says, how unprofitable is this technology? How much would we have to subsidize it to get it to be used? Okay, so this is not uncommon. Or think of trade link. This is, exports of a good from one country to another. It's just unprofitable, and so then the equilibrium value of that export is 0. Case 3 is sort of the opposite of that. Maybe the supply curve lies everywhere to the right of the demand curve. So again, there could be a crossing now at a negative P. I guess sometimes we have sort of like a negative price. You have to pay to get rid of something, but that should be specified as a different activity, actually a disposal activity. So the correct solution, economic solution to case 3 is that the price is 0. Complementary variable is 0. Even at a 0 price, supply exceeds demand. We don't run into this much, but things like quotas or pollution permits can have this solution where there's just too much of a supply. The quota level or the number of pollution permits is greater than the number demanded even at a 0 price. So you just flood the market with, and the European emission scheme came close to this a few years ago, right? The price of permits were effectively 0. People were buying them up at a very low price, just speculatively. So this case does arise. It's not nearly as common as case 2, but it can occur. So my simple view of KKT, and I think Tom can correct me on this, is the way that these things are handled in the MCP solver is KKT says, well, you add a number of added variables and added equations, and you convert the inequality nature of the problem into actual equations. So you put in these slack variables. So marginal cost minus price minus slack 1 equals 0. With the added equation, there's an added variable. You need an added equation. The added equation is that S1 times X equals 0, meaning one of the two has to be 0. And similarly for the demand side, excess supply, X minus D of P minus S2 equals 0, with the complementary condition S2 times P equals 0. And now these are a set of equations. Okay, and I think this is basically how it works.
And you can see S1 S2 reported in the
yes, yeah, I'm going to show that on this one in a second. Yeah. Okay. I think this is something you're probably never going to care about, but it does teach something that caused me some angst. I had to learn all of these things the hard way. I'm telling you stuff in 2 minutes that took me hours of angst and anger and yelling at my computer and stuff like that. So this is just a real stylized example of then what the computer does. This is a very simple, what's called a Newton method. And I guess goes back to Sir Isaac himself in finding solutions to nonlinear problems. So this is an example of a really crude, simple Newton method, but I think that's still kind of an idea that underlies what goes on in path, right? Okay, so the thicker curved line is a function. It's excess supply at price P minus D of P. And what you're trying to find is the 0 of that function. And you're trying to find a solution where that's 0. And that's the P star that's indicated right there. That's the solution, but it's a complicated implicit function. We don't know, we have no idea where that solution is. Okay. So how can you try to solve the model? Well, basically what a Newton method is you make an initial guess. And you say P dot L equals this. Okay, you just make a guess. And then what the algorithm does, a simple algorithm was done, was calculate the excess supply at that price, okay, and calculate the slope, E prime of P at that price, okay? And then by the equation of a triangle, your next guess is gonna be P1. So what it does is at E of P, you follow E prime of P down to this zero value down here. And just from the equation of a triangle, it means your new guess is the old guess minus E prime of P inverse times E of P. So that's what you call an iteration rule, right? So it computes the new guess there. And then it just repeats. So the second guess is going to be down, then you compute E of P at the new value of P, calculate the slope, and you go up, and that's going to be your third value. And you can see that if this thing is well enough behaved, it's going to converge to E of P.
The key,
At speed.
this is for the nonlinear equation version of the model. You don't know anything. The key innovation in the complementarity world is that you get the direction locally, but then you're going to decide you go along that direction so you hit a boundary. And the key innovation is this idea that you follow the direction down to where a boundary gets hit. And so that's the sort of the wrinkle here. And this actually goes back to, again, it's the same thing that Karush was a master's student here in Chicago who came up with the control conditions. And then there's a student of Stephen Robinson. Stephen Robinson is another faculty member of math in Wisconsin. And his student was Josephine, who came up with the idea of this path following. And there was a master's thesis here in Wisconsin. And both Josephine's thesis both inspired both Ferris and Lars Mathieson, who I work with. Were both inspired by that work. And that's this idea that you take the Newton method, which tells you the direction to go, except then when you're following that direction, you find out where you hit a boundary and then you adjust. So the boundaries are respected in choosing where the next iteration is. So that's what makes it a little more complicated.
Yeah, also, yeah.
Yeah, it's a nice diagram.
It took me 10 times as long to make the diagram as to explain it. I did this years ago. I've used it many times. At this point, I've recouped my investment. And by the way, at the bottom, this generalizes to many equations, okay? P becomes a n/1 vector. I shouldn't say E prime of P, it should be E sub P of P. The Jacobian matrix of the n excess supplies, has to invert that matrix. And then E of P again is an n/1 matrix. So I actually did this in the 1980s before, just when I first met Tom and didn't understand that the mathematicians were much smarter than me. And I actually wrote a program to do seven of these and 7 unknowns. And I got it to work, but the boundaries were, I wasn't getting the complementarity very well.
Well, the thing the complementarity world and the equilibrium models throw at these problems is that not only is it, you don't know exactly which equations are binding at the solution, so you don't know exactly the size, but the dimension is of that Jacobian. And then on top of it, generically, the problem we're trying to solve is singular at the solution, because the place level is determined as part of the solution. So we make all sorts of challenges for this problem. The problem class we're working on is particularly nasty. But we don't have to worry about that. We can solve it.
Yeah. Oh, thank goodness. I don't want to waste my life. I was programming in Fortran, that 7 equation model. Okay, so the other thing I want to say about this diagram is just two things to keep in mind if you're making up your own real simple models to try to understand how things work, is that there's two features of these things that are important. The first one, if you take this algorithm literally, is that function E of P has to be differentiable. Right? And so there's certain classes of discontinuous functions or with kinks. Can you deal with kinks? No, it's good.
No, the kinks have to be built in.
Yeah. Oh, yeah. Okay. So you need a kind of smooth function here. The second thing is the importance of a starting value, which I alluded to earlier, and you can see it. Suppose you don't set one, so the starting value is P equals 0. Okay. Well, and this is realistic from an economics point of view. If P is 0, E of P could go off to infinity. You know, supply just keeps going up. Supply 0 and demand goes off to infinity or something. And so it can't compute E of P, and there certainly can't compute a gradient at E of P. So these starting values in nonlinear problems are important. The other message.
There's a question here about, yes, the point that the one here made is that the numerical analysts don't compute inverses, that's true, but they solve the system typically using some sort of factorization. This factorization system that's used in math, you actually have a choice of factorizers. So you can choose which one. The one that's been used, I think, historically has been LU-SOL, which is by Michael Saunders from Stanford. But there's a new factorization system that they have for the group in Florida State that's extremely fast as well. So you have some choices here about how to do it. But it's correct. You never solve the inverse explicitly because it's in the GAMS version of this where you have n-dimensional. N can be typically a typical application would be around 50,000. And so it's a big system. And you rely on solving systems which are inherently sort of sparse. So these factorizers are designed for solving large dimensional sparse systems and accounting for them. So what you're getting is a very good nonlinear solver together with a method for identifying what the active set is. So just give you a feeling about what's in the background.
Yeah. So, right, you can forget this for the rest of your career probably, but starting values and continuity are important for making it work. And then just quickly, there's, if there's it could be a corner solution where excess supply is positive in equilibrium at the solution, and the complementary variable P is then 0. So this would be a case where that occurs. And then again, this little vertical squiggly thing, S, is the slack value of the slack variable. That's the imbalance in the equation at the solution. And we're going to go through this, the supply and demand problem now. So let me do that. I think the timing is working. It's working well. And we'll have our break at 10 o'clock in the Central Time. So there's 4 parameters in the model. And then you can use the slash notation to assign initial values, or you can just say equals, semicolon. 2 non-negative variables. NLP is not useful in this problem. 2 equations, supply and demand. Those are the 2 equations written in the correct direction. Supply can be strictly, demand, marginal cost can be strictly greater than price in equilibrium, and supply can be strictly greater than demand in equilibrium. So all those slack variables are created by the solver and the complementary conditions as well. So all we have to do is say which equation is associated with which unknown. So supply.x, demand.p. And then tell GAMS to solve the model. And then there's two counterfactuals. One is to increase A, which is the intercept of the supply curve. So demand, we're moving the supply curve up. That's going to be case 2, or move it way, way down. And that's going to be case 3. Okay. So maybe I'll just go to, so let me explain then what the output of these 3 cases are going to look like. Because these marginals are really valuable sometimes. They tell you how unprofitable something is or how much excess supply exists. So when we solve this model, and we'll do that in a second, in the first, you go down the listing and you click on the first solution value. And this is what it's going to tell us. It's going to tell us GAMS reports 4 things about variables. The lower level, the solution value, which is called level, the upper bound, and the marginal. If you declare something as a non-negative value variable, the lower value is automatically set at 0, and the upper value is set at plus infinity. You can set other values because of this KKT, the way that translates the model. You can put bounds, any bounds on variables. It doesn't have to be 0. You can have an upper bound. This is an interior solution, right? It says that the solution is price 4 and quantity 2, and the marginal is 0, which it should be. All right. If you have an interior solution, then the weak inequality holds as an equation, and the marginal is 0.
Just a GAMS notation introduction. Today's mainly our target audience here, people who may not have seen GAMS before, so kind of help you sort of get oriented. There's a lot of, I say GAMS is complicated, so it takes time to get comfortable with it. But I would say that the best way to learn GAMS is to work with little tiny scalar models. That's exactly what Jim is illustrating there. So no fancy syntax, just the basic stuff. So when you work with a small scalar model, here in the solution listing, you see there are 4 columns, and those are 4 numerical values associated with a given variable. 2 of them are model inputs, that's lower bound and upper bound. And those would be assigned through either the way you declare the variable, you say it's non-negative variable, it will automatically put in a 0 and a plus infinity, or you can assign them. And the way you assign them is P dot LO is the lower bound, or P dot up is the upper bound. Right? So those are numerical values tied to that variable that you can assign or read. And then coming back to the solution, you have 2 additional variables, the level and the marginal. And the level is going to be dot L, and the marginal will be dot M. The idea is you're using the variable as a symbol in the declarative structure to declare the equations. And then GAMS, after you say solve, it comes back and gives you numerical values back. So that's what you'll see going forward. So I just wanted to interrupt just to give the ones oriented to how this actually is organized.
Right. And this is also because there's these 4 numerical values stored. When you want to display a variable or assign a parameter to a variable, you have to tell GAMS which of these 4 things you want associated with that display state. So you have to say like x dot L, because otherwise, which one do you want? Which of the 4 do you want? So I forgot to mention that back with some of the code. Well, you'll see it in, never mind. Okay.
So the one thing I've just add also, when you assign a variable, you can assign a lower bound and an upper bound. It also gives you this shorthand. This is just dot fx. It says dot fix a variable. So if you want to have a variable of a fixed value, you basically drop it out of the optimization process. That is equivalent to assigning the same value to both the lower bound and the upper bound. So assigning dot low equals new value and dot up equals value is the same as dot fx, dot fix. So that's the basic one, the key. Those 5 suffixes are the ones
Yeah.
that most commonly used.
Yeah. And then the solver will automatically drop the equation associated with that variable from the model. Because you're essentially you're making that variable a parameter effectively. So it drops that, but it still will report the margin, and which is very useful. So I like that. I like it that they did that way. So again, from the complementary, if you remember back, sorry to run back here. This equation says that the level value and the marginal should never both be non-zero. And so if that's not the case, it's probably not a valid solution. If you look up, it'll probably say non-optimal or infeasible or something. So then the first counterfactual, where the supply curve is moved way up, this is what's reported in GAMS. There is a price reported. That's the demand price. However, the good is not produced in equilibrium. So the level value is 0. That's the dot there. GAMS just decided that's, we know that's 0. But there's a positive marginal. And that positive marginal, the value, the numerical value of that is exactly this. Okay. It's the imbalance in the equation or the inequality at the solution, okay, which turns out to be exactly 1. It's not an indicator 1, it's a numerical value of that solution. The third case then, case 3, is where we move the supply curve way down, and so it actually intersects the x-axis to the right of the intersection of the demand curve, where demand is 0. And here's what GAMS reports back. There's a positive supply of 7, but the price is 0. And again, the marginal is the numerical value of the imbalance in that equation. It's how much excess supply there is at the solution. So if these were pollution permits, it's how many of these things you have to buy up for the price to go 0. So these marginals in lots of problems can be, I think, extremely valuable for answering economic questions. Maybe it'd be better to run them. I was going to just indicate this for future without, you don't have to remember this, but I just thought I would just mention this third solver, the MPEC solver, which allows you to optimize over some variable, which I call an instrument variable, subject to a constraint set, which is an economic equilibrium problem. And so that's very cool. So in this problem, I put in a tax rate. So tax revenue is the amount supplied, it's marginal cost times the tax rate times the output is the amount you collect. And there's a new supply equation. You can still use the old demand equation, which says that marginal cost times 1 plus the tax rate is price. So it's an ad valorem tax that's taxed on. So an example of an MPEC problem is that you have an objective function that's not matched to a variable. You see the model declaration. And then supply 2, this new supply equation is matched with X. And the demand equation, we don't need to rewrite that. That's already in the model. That's matched with P. And this is an example of trying to find the optimal policy instrument, okay? Which is to rip off the taxpayer in this case. So solve tax revenue using MPEC, maximizing the variable tax revenue. And so this is really useful. I've used this to optimal level of infrastructure, optimal level of public consumption goods, optimal pollution tax. There's all kinds of applications of this in some of my my model list. This is the solution, the optimal tax rate. I wouldn't have guessed what it was. It's 2/3, 0.667, and the tax revenue collected is 2.
There's a question in the chat. Questions online? I hope this is, our idea today was to try to get people, to reach out to people who haven't done this stuff before. And this is a really great opportunity to sort of get a sense, get oriented toward what we're about. And we'll come back in half an hour. We'll take a break for coffee here, and then we'll come back and we'll have a little bit of a programming exercise at some point.
I have my examples, which are still called Kiev 1 to Kiev. So Tom and I taught a course in Kiev, Ukraine last August. And so we are feeling the pain of Ukraine more than most Americans, I guess. And we had a wonderful, wonderful time there, 9 or 10 days.
We'll see everybody have that.
Okay.